Awesome. So we're gonna get started. As a little bit of a preface, this was modified off of a talk that I gave for Purdue First Forums last fall. That's an event where they have a lot of mentors up at Purdue that come in and give different talks about FRC related topics and FTC topics. So that's modified off of this one, but then a little bit more tailored to our team in particular. If you don't know who I am, most of you probably do. My name is Jonathan Heidegger. I'm a sophomore studying computer science up at Purdue. I did 2 years of FLL and then did 4 years of FRC on 3176. And then some of the things I do up at Purdue is I'm in the marching band up there. Talking about drivetrains first. So in FRC, there's a lot of different types of drivetrains that we can use. To start off, we've got tank. This is the simplest and the most robust option. We have Mecanum, which uses these really interesting Mecanum wheels. We've got Swerve, we've got Omni H drive, and then we've got a lot more. There's the field of FRC drivetrains has evolved a lot in the past. From a historical perspective, drivetrains used to be one of the most challenging parts of the bot because there wasn't the Andy Mark kit chassis. So before that advent of a lot of the COTS products that we use now, building a drivetrain was a huge task just to get your robot to move around. And now a lot of what FRC drivetrain is being able to finesse and really iterate on some of the finer points of these drivetrains. So we're going to kind of go in and talk a little about some of the basic ones before we get into Swerve. So like I said, tank, you can see over here we have the Andy Mark kit chassis. It's simple, robust, and efficient, and it's gonna work. We have 2 sides that are controlled independently. So even though we have 4 motors, we have just the 2 sides that we're gonna control because we're gonna send each pair of motors the same command. And then when we want to turn, we'll send them different commands so that they actually turn. And that's called skid steering because the wheels actually on the end here are going to skid along the ground. Because if you think about it, if you're turning around the center of the robot, these wheels have to almost move sideways, which then they're not moving straight in, and that's why we call it skid steering. And so some of the limits of this are when you're driving this type of robot, you have to worry a lot about how you're oriented because that determines what path you can go. So if I am trying to push on a defender, it's going to be really hard to try to get around a defender if they are pushing at the side because I have no way to counteract that force. If a defender is pushing on the side, I have to try to get around them, and there's no way for me to actually push against that. Then we have Mecanum. This is a way that teams can have more freedom in the way that they move their bot around. So they use this type of Mecanum wheel, which is you have little rollers that are all slanted at a 45-degree angle. These were used to have to be custom made by each individual team in the mid 2000s, and that's when Mecanum bots started to show up a little bit more and had some more prevalence because they were a really cool idea. Because instead of where a tank wheel is just going to interface with the floor like you'd expect a wheel to, these actually the where they apply the force onto is at angles. And by doing that, if you can control each one independently with a little bit of slippage, what you can do is you can have your robot move in any direction, including sideways. And so that allows you to move around a lot more freely. But Mecanum wheels, because they have all these rollers, have a lot less pushing force. So if you're trying to play defense with a Mecanum bot, you're going to have no pushing power, and that other bot can just push you wherever you want to go. So Mecanum bots, they are interesting to look at and to kind of see, but from a general perspective of being competitive on the field, they're not usually recommended. So let's get into kind of the meat of what we're going to be talking about today. So what is a swerve drive? So Swerve, in similar to how Mecanum has individually controlled wheels, Swerve individually controls every wheel, but every wheel is going to have a module like this, where you control not only how fast it spins, so in Mecanum you control how fast each wheel spins. This you can also control the orientation of each wheel, so you set where the wheel is actually pointing. And this allows your robot to translate and rotate independently. So just like the tank can either be going forward or it can be turning. With a Swerve bot, you can do both. And so that's where the 3 degrees of freedom come in, is you have forward, backward, left, right, and then your turning motion. All are independent. And you can have full power in any direction. So if you have a defender that's trying to push against you, you can turn your wheels and push your full force of your drivetrain into that defender. So it's really flexible, both on playing against defense and playing defense on other robots. It allows for a lot of flexibility on the field, and gives you the power where you need it. So let's talk a little bit about a Swerve drive done well. This is an example from our team. So we're going to be watching a match video.
3, 2,
we are over
1,
here.
Power up!
And our teams are off 4103 racing across the field, as is 5403. 5403 Luminosity successful in placing a cube on the scale for the Blue Alliance. 2867 a little bit off with their scale auto, but 7.
So you can see with that, in autonomous, able to keep the facing of the robot consistently pointing at the other side of the field while navigating through this zone to be able to score two of the cubes into the switch. So that was an example from the 2018 Swerve drive that Team 3176. Awesome, thank you. So yeah, so this is LancerBot. This bot has a total of 3 controlled parts, 1 for each side, and then the arm in the center. This was very effective at the game, but from a mechanical and programming standpoint, pretty simple to execute. Everything was open loop. It was all written in one C file. It was pretty bare bones. So this was our 2017 bot, so a big step up. This was Chimera. This we designed a custom plate that connected this COTS Swerve module through chain, and then we had 4 of those, and we were able to design and build our first Swerve bot. This was a very interesting season. There were a lot of lessons learned from this season. Some successes. This was our first year that our team won a blue banner at state and advanced on to Worlds, but this was also the year that we had the most amount of dead time on the field, the amount of times that we were either disabled or that our drivetrain failed. So it was a big learning year for the team, and we're going to talk a little bit about what some of those lessons were as we go through. So this is the Swerve pod hardware from 2019. So this is one of the most updated versions of what the hardware is. So you can see we have the PG71 motor, and that's responsible for steering. And then we have either a Neo or a Sim motor on the drive. And so this goes through a gearbox, and what this gearbox does is translate the torque from those into the Swerve module itself. And then the Swerve module has this outer gear that actually spins the module around, and then there's an inner shaft that's driven by the Sim or the Neo, and that goes through this linkage down through to actually drive the motor itself, to drive the wheel itself. So that's how you can have independent control of the steering and the motor. And then from an encoder standpoint, we either use the SRX mag encoder usually for the steering, and that would be this enclosure on the bottom, holds one of the encoders to the PG71's output shaft, and then using either the Neos to count their internal clicks, or we go with another encoder that would sit on top. That's how we did it in 2018. So that's kind of the hardware of what the Swerve pod was. But originally, this was our original pod design. You can tell from a mechanical design perspective, it's a little bit different since we had the motors inverted. The fun thing about this pod was that it had about 1/8 of an inch of ground clearance, which is not great. So if you run over anything, you're about to take all of your wires out of these 2 motors. So the PG71 was riding 1/8 of an inch above the ground, and that was interesting to say the least. We also used a quadrature encoder on the PG71. So what that means is we used just the built-in encoder, which all it does is relative. It knows from where it started. It counts the number of ticks since it started. So that means if all the wheels started in the same position, that's fine. We know what the homing position was. But if one wheel maybe got twisted when we were setting the robot down, or maybe we forgot to set all the wheels, then that meant that it didn't know where it was. The RoboRio had no way of understanding where these were. So originally at the first competition, we decided we're just going to set all the wheels. Every single time, we will hand place every wheel before every match. And that ran into definitely some issues because you have some error of hand placing them, and you have to have and remember to do that before every single match and be very gentle when you set the robot down. So that led to quite a few issues. So then our next solution was to home the wheels. So this meant that we had to have another sensor that was actually going to tell us where the wheels were. So we had a magnet attached to the corner of the pod and then a Hall effect sensor. So a Hall effect sensor is a magnetic sensor which you can set to just trip after it senses a certain strength of magnetic field. So what we had is we'd have the Hall effect sensor sitting on the underside of this plate, and then the wheel would spin around. We would spin the position until it sensed that magnet, and then we knew, okay, that's where we should start counting. That's our 0 position. The thing is that the magnetic field strength, the accuracy of these little 50-cent sensors, they weren't the greatest at being able to give consistency. So you still had about a plus or minus 5 degrees, and you had to do it at the beginning of every match. So in autonomous, we would sit there for 3 seconds while all of our wheels homed before we could do anything. So let's watch a video of that. This is actually from the 2017 state championships. So we are in red. We're going to be in the corner delivering a gear. So we're right here. And we start waiting, our wheels are homed, and then we can start going. And so that year we were also restricted from our accuracy if we could only do that short little auton because we didn't trust the way that our wheels were homed to do anything other than that. So some of the more advanced autons would have come around to the side or done other things on the field, but because of our accuracy losses, we could only just do that. Is everyone still on to the PowerPoint? Did it freeze on the video that time?
It did not. We are on the PowerPoint.
Awesome. So then for the pods 2.0 and 3.0, we switched over to Talons, which allowed us to use the Talon mag encoder, which has a different type of magnet. This is called a diametrically polarized magnet. So a normal magnet, what you'd expect is North Pole to be up here, South Pole to be up here. But here, if you have a polarized magnet that you have South Pole on one side, North Pole on the other, you can now have another type of sensor that's more accurate than the 50-cent Hall effect sensors sitting on top. So this is in the shaft that's spinning, and you can sense the way this magnetic field is moving and where it is, and actually know the absolute position without having to do any homing. So that meant we could start immediately and have that auton that we showed at the beginning to start immediately and start going. And these are much more accurate in their absolute position than our Hall effect homing solution was. So using the SRX mag encoder was a huge step forward in being able to know the absolute position of the pod and be able to get running. Now, a couple things for electrical considerations. You need to have a robust electrical system if you're going to do Swerve. If you have any one wire missing, the entire system can go down. So the first year we did it with all Victors. This is the example of what not to do. So you can see the amount of Victors we have just sitting there. And every Victor requires a control wire. Every encoder required 2. So we had 4 encoders for 8 wires, and then 4 for each of the Hall effects. So that meant 20 control wires, all having to come into the RoboRio, and all having to work. If any of those got unplugged, then the entire system would not work. And so talk about adding points of failure to your electrical system. A funny story about this robot right here. we pull into our first competition, ready to go, and we're going through inspection, and that part of inspection that we all think is just, we take for granted, the grounding test, we failed that. So somewhere in our system, somewhere in our electrical system, there was a short to the frame. So that meant, in the pits, pulling out every single wire from this. And this is after we organized it. So this is a photo of after we organized it. So imagine before, pulling all of those wires out, then testing each individual one to figure out where the short was, and putting them back in. It was a nightmare. So the second year that we did it, we did Talons, which was a godsend because everything was on the CAN bus. All the sensors were integrated into the motor controller themselves. So then all we had was the single CAN wire from the RoboRio going into your CAN loop. And that was a much more robust system, and it had less points of failure and was easier to find where that failure was when something happened. So now let's get a little bit more into some of the software and controls. So we're going to focus first on what the Swerve pod individually does before we talk about a system level. So the pod is going to be given a position and a speed to go to. So some angle that it has to go to and some speed. And so the first challenge that the pod has to figure out is what is the quickest path to get to that angle. So let's say we're at this red angle here. We're at 90 degrees. And I want to go over to this angle over here. Let's say it's 300 degrees. Now, if I just was computing, well, I'll just do where I need to go minus where I'm going, that math is going to take us this long way around, because that's the shortest distance to it. It's the only way it can go. Where, in fact, if we can cross over 0, there's a faster route through here. So that is if we always have the wheels going forward. That is one way to solve that. If we look at the way the code can work, this is an example of find steer position. So this is what it has to do. So we're going to get the encoder position, which is going to be the steer motor. We're going to get that selected sensor, which basically is the mag encoder. We're going to minus it by some constant because we just insert that magnet into the shaft. It has to be calibrated one time. And then we're going to convert to radians. And we get that error of where do we want to go minus where we are. And so there's a couple different ways we can think about where this logic is. So the first is if it's greater than 3 pi over 2, which is if it's greater than 270 degrees, then we know we just need to go the short way around. So what this is we just need to go the short direction in that way. The other one is if it's less than 2 pi over 2, which means this is, I just have to go the other way. And so the other thing that you can do with this is, with this command, you can actually reverse the velocity set point. So that's what this is right here, is if instead of going this way, if I just turn to the opposite and then reverse my motor power, that's going to give the same effect because I've flipped the speed of the wheel and it's going in that direction. So there's a lot of different ways that you can figure out what your wanted angle is. The first step is I'm just always going to go clockwise, and you'll always go clockwise to the solution. The next one is, let me figure out, instead of going the long way around, I never have to go longer than 180 degrees. So that's the next. And then finally, if you can reverse your motor, you never have to actually travel more than 90 degrees. If you can convince yourself in your head how that works, that's a really interesting problem with Swerve to look into. And then let's talk a little bit about, from a large perspective, if we have to control 4 of these, now we have to have it's like we're driving a car with 4 steering wheels and 4 gas pedals, because we have to set each one's position and set how fast it's going. And so that would be insane. If that's what the driver had to do, imagine if they had to be computing all of this in their head. But luckily, we have software that can help us. So this is actually how we control the Swerve robot. So we do it with the right stick. This is your forward and backward and left and right. So they command the translation of the robot. And when I mean translation, it's basically, are they going forward, backward, left, or right, and any combination of that. And then the other stick, its x-axis, is for turning. So if I push this stick to the right, I'm going to turn to the right. And these are independent actions, so the driver can go forward and spin at the same time. And so this is a lot easier for the driver to comprehend. But now that adds an extra bit of code for us to figure out. We have to convert what the driver wants into what the robot has to do. So we've talked about the drivetrain a little bit. One way we can do this is with object-oriented approach, which is basically we have different classes that are going to help us. So we'll start at the Swerve pod at the very bottom. So we have a Swerve pod class that holds 2 motor controllers, and it has to figure out where it needs to point itself given a high-level command and how fast to run it, doing a PID loop on both the position of the pod and of the speed of the wheel. So the Swerve pod is its own contained little piece of code that's going to be copied 4 times because we're going to have 4 instantiations of this Swerve pod class. And if we go up a level, the drivetrain is going to own 4 Swerve pod classes. So the drivetrain doesn't actually directly control any motors, which is really cool because it allows the drivetrain to do some more advanced stuff. And for your bug testing and trying to figure out where errors are, you know if it's with the motors, it has to be in the Swerve pod level. So the drivetrain, it computes your swerve drive, and it looks through and it does a lot of the high-level stuff, and then the robot class owns a drivetrain. So that's the benefit of object-oriented programming, is it compartmentalizes your code and makes it so that when you have errors, you know where to look for them, and when you want to add features, you don't have to worry about breaking things. So a little bit more history about the team. In 2017, the first year we did this, we did it all in one C file. So Swerve in one C file with function calls. So that C file was about 4,000 lines long, and it was a mess. We couldn't edit any of the Swerve code after about halfway through the season because it was so convoluted that any edit would have huge repercussions on the rest of the code. So that meant we were limited on how much we can improve the system because we were constantly scared of the system. Where in object-oriented, you don't have that problem as much. Because if I mess something up in drivetrain, I only mess up what is in this box. It doesn't spill over, and it can help you make sure that more people can work on the code and that everyone knows where things are. So let's talk a little bit more about how the drivetrain works. So it manages the 4 Swerve pod class instantiations that it has. And we'll talk a little bit about, but it can do different command types. So robot-centric, field-centric. It can, if I say, I want you to go forward at 100% power, it'll do that. Or I can say, I need you to go forward at 10 feet per second. It can do that as well. There are a lot of times when you want to control in percent power, like for example, when the operator's controlling it. When you have a driver that's physically controlling it, they're not thinking in their head, oh, I need to go 4 feet per second, then I'm going to reduce my speed to 2 feet per second. They want to say, I should go about 50% of what my max speed is. And so that translates easier. But in autonomous, the computer can think about, oh, I want to go exactly 3 feet per second. And so having a mode to control in both is super helpful. It calculates the set point for each swerve pod and sends that out, and does some of the brownout protection. So you can see this is what a brownout looks like. Is you have your voltage dropping dangerously low, getting into that 7 volt, 6 volt territory. So what's the difference of robot versus field centric? Robot centric is when if I push forward on the stick, the robot goes forward. If I push to the right, it's going to go to the right when you are on the robot. So it's all in reference to the robot. Where field-centric, if I push forward, it's going to go in reference to the field. It will go forward no matter the orientation of the robot. So robot-centric is really great when you need to line up or when you're doing something that is in reference to the robot. So when you're watching a camera stream as a driver, you want to use robot-centric because that's how you would naturally think about it. But field-centric is really great for large motions across the field because it allows the driver to take a step back, and instead of worrying about the micromanagement of how they're getting from place to place, they can think about large strategy moves and being able to be more strategic in how they move about the field without having to worry about the minutia of which way are they pointed. And so field-centric is when you usually what you spend the most amount of time in when you're driving, and robot-centric is used for some of those last little bit of lining up at the very end. A couple other notes on what brownout protection is. Brownout protection is important for any robot, but is especially important for a Swerve robot. You go from a normal tank bot might have at most 6 motors on it, and that's if it's a really powerful tank bot. But a Swerve bot at a minimum needs 8 motors, so you're already 2 additional motors over a tank bot. There's 2 places you can implement brownout protection, and the first is the most common, in the Swerve pod itself. So in the Swerve pod class, you add ramping to the drive motors, because the biggest thing that causes a brownout is when a motor goes from full forward to full reverse. Because a motor requires current to be able to switch. It actually will stall for a little bit and then will go into full reverse. And so that stall to stop it and then go into full reverse requires a lot of current. And basically, if you pull a lot of current, you're going to trip one of your breakers or you're going to brown out your system. And so brownout is basically when the RoboRio is not receiving enough power that it shuts down and reboots. And that usually takes about 20 seconds to reboot and reconnect your robot. And so that's a lot of time that you're dead in the water. The other place you can do it is in the drivetrain. You can do some more advanced things where you actually calculate what the max power of the system can handle, and then understand, because each Swerve pod, it only knows about its own little environment, where the drivetrain knows about all 4 Swerve pods. So it can make more informed decisions. It can say, hey, you Swerve pod 1, you can use some power right now, because I know Swerve pods 2, 3, and 4, they don't really need it. And so it can be more dynamic in how it allocates its power. And so that's another option. But the first, most basic way is add ramping to your motors. You need to do that if you're going to do a Swerve bot or a tank bot, because those stall current loads are what are going to kill you. And the biggest thing is with all these new motors, they draw an incredible amount of power. Falcons can get around 700 watts when they're at max power. And if you have 4 of those going, that is a lot of power. So being mindful of when you need the power, you can use it, but also knowing that having systems in place to protect your own system from itself. So now let's get back to the final question. We've kind of been beating around the bush, but how do I know where to point the wheels? I get some of these high-level concepts, but where do we actually point the wheels? So for this, we're going to need to do a little bit of a math review. So we're going to talk a little bit about vectors. If you haven't had vectors in school, don't worry. We'll try to give you a little bit of an intuitive understanding of what they are. The things you just need to know are that a vector represents a direction and a magnitude. A vector is basically represented by one of these arrows, because this arrow has a direction that it's pointing, and it has some magnitude, how long it is. And that's the basics of what you need. It has a x and a y component. So this orange vector is made up of this green vector and this red vector, because this green vector points just in the y, this red points just in the x. And the final thing is when you add 2 vectors together, it's the same as just putting the vectors tail to tail, head to tail, and that you can add them like that. So if we go through, if we have vector 3, 1, that's going to look like if I go over 3 and then up 1, that's what that vector represents. If I have vector -2, 2, go -2, then up, and that's my orange result vector. So with Swerve Drive, we can think about the command that the driver is giving as some vector, because they're pointing the stick in some direction. So you can almost think of wherever they point the joystick, that's the direction of this arrow, and how much they point the joystick, that's the magnitude. So that's our vector, our velocity translation vector v, And then the rotation vector is basically how much they've moved the other stick side to side. And that we use this symbol that looks like a W. It's called omega. That's for the amount of rotation. That's the rotational speed to be exact. And so for each individual wheel, we need to determine the angle and the speed for it. So let's talk first about translation. We're not going to turn first. So if I want to go straight forward, how do I point my wheels? I can, well, this one is if I want to go straight to the right, I would point them straight to the right. Now let's say if I want to go in this direction, all I have to do is point my wheels in that direction. And that is how you do translation, is you take whatever input vector and you point your wheels in that direction, and that's going to determine how you point the wheels for translation. Now what makes it interesting is if we add rotation. So let's first do rotation independently. So if I want to turn, how do I point my wheels? Because we're not going to turn like a tank bot because we have the power to move our wheels. So if I wanted to move them, I'm going to move them in the way that this is going to rotate, which is a circle. So if I draw that circle and then I point the wheels in that direction, that's going to be how you can turn without your wheels slipping at all. So we're not skid steering like a tank. We actually can put our wheels in the optimal path to turn the fastest. Now, here's the great thing about vectors, is we've done both of those independently. All we have to do is add them together, and that's our final solution. So I'm going to add the rotational component to the wheel that I want. I'm then going to add the translation point, that green, and then I add the vectors together, and that gives me that red output vector. So that is where I actually want to point my wheels. If I do that for all of them, we'll get the actual end goal of what those wheels are going to point with. By individually calculating what wheel needs to point at what, we know that that's going to give us both the rotation and the translation. If you want to dig in more to this, Ether's Swerve paper is the single most, it's the best digestible way to get into this. It's what we used to actually program it back in 2017. It's very, very readable, and I would highly recommend going and checking that out. So a couple more takeaways from our from 2017 and from all the other seasons. The biggest thing that you can do to increase your robot performance on the field is have a physical checklist. You need to, when you have a complicated system, there will be mistakes. And so you want to have something that can help you check for that. So a checklist goes through and it will go through every single mechanism. And you will make sure that it works, and you will physically check it off. And that means when you get on the field, you have a much higher probability of things going on. The checklist saves you matches, because if you forget to plug something in or something coming unplugged that you didn't notice, you'll be able to figure that out before you get on the field. And with Swerve, if you have a missing CAN cable or a sensor came unplugged or something, you'll be able to see that very quickly in a checklist instead of trying to diagnose a problem while your robot is stranded on the middle of the field. Swerve is a great fallback defense. So even if the mechanisms on top are not performing the way you want, Swerve can outmaneuver and can push better than any other drivetrain. So it means it is the best at getting around defense and is one of the best at playing defense. You can push with your full force anywhere, and that means you have a much higher pushing ability than a tank bot. And you can apply your lessons from this year into the next year, because Swerve is this iterative process. So we're going to talk a little bit more. Basically, should you do Swerve? This is kind of a general to any team, but it's good to think about for us is start in the off season if you're going to do it. And make sure that you use COTS if this is your first time doing it. Leverage the existing libraries. Understand that there's a lot of really cool things with Falcons and with Spark Maxes and with Talons that you can leverage those existing tools and then commit over many years to improve it. But the biggest thing, do not lose sight of the mechanisms on top, because your drivetrain is awesome, but it's the mechanisms on top that win you. There's a quote that was in the 1678 strategic design that really resonated with me, and it's, "A drivetrain will not win you an event. It can only lose you an event." So if you think about that, a drivetrain can help, but it is singly not going to win you the event. But a drivetrain can singly lose you an event, because if you cannot move around the field, you are not going to do well. But here's more of the argument of why you should do Swerve and why the team should do Swerve. So the biggest thing is student engagement across technical teams. This is a complex system that has many problems in mechanical, electrical, and programming. And it's requiring all of these things to come together to design a correct and efficient system. So it requires communication, it requires challenges in every single aspect of an FRC team. And it's an amazing learning tool that, as a goal to build a Swerve bot, you're going to gain more appreciation. Even if you just do the programming, you're going to have more appreciation for the electrical and mechanical work that went into it, because you have to understand and have ownership over that so that this system comes together. Another thing, it's a statement on the field when you show up with a good Swerve bot. And there's a brand identity to it. And I think we realized that a little bit this year, that the team, our team in particular, can become known for this. And that when we rolled up to that first event and we had a couple people coming around to our pit and they were like, "Oh, you guys didn't do Swerve this year." That shows that we have the brand identity in Indiana, that if we do Swerve well, it becomes a statement and becomes something that separates us and makes us interesting and something to go watch. One thing is it can be easier to drive. I say easier in quotes because every drivetrain just requires practice, but you don't need to have as much finesse in understanding how a tank bot works, because it's not as limited as a tank bot. If I'm driving a Swerve bot and I actually orient myself wrong, it's less time to fix than in a tank bot. Take, for example, this year, lining that hook up on the bar. That required, for the climb, required a lot of practice and making sure that you did it right. And if you did it wrong, it required a more complex maneuver to fix it. Where in Swerve, if you were a little bit off, that's a much easier problem for the driver to fix because they can move in any direction. One other thing is Swerve automatically increases your potential for awards, technical awards. It increases your system complexity and ability to talk about it. And if you've taken the students along for the journey with this, it allows people to talk intelligently about not only manufacturing design of how do you design a system, how do you design a robust system, how do you program stuff. You need control loops for this to work. And so it puts you into a category of being available for some of those awards and immediately unique. And again, that's one of the big things, is if you are unique, you are more likely to win awards. And it is one thing that is the easiest to improve year to year. You are always going to have to move around on the FRC field. You don't know maybe what you're going to have to do on that field, but you are always going to have to move around. So time spent investing into the Swerve system is going to pay off in the long run, because it's something that you can continue to work on and iterate and learn from year after year. Now we're kind of going to open it up to kind of an open questions. Were there any questions over anything we went over? Anything on Swerve, anything on how the team designs stuff? It's open questions now.
What is your opinion on triangular Swerve drives? Kind of as a joke.
Yeah, triangular Swerve drives you can do Swerve with any number of wheels you want, but I would not recommend triangular Swerve. There is a type of drivetrain. If we go back to types of drivetrains, there's something called Kiwi drive. I did not list all of them because there are so many different types, but there's a thing called Kiwi drive that has 3 omni wheels in a triangle. And the biggest thing that people recognize is it's kind of a joke, but Simbots in 2015 built a Kiwi drive robot that did very well at championships. So maybe there are room for some interesting non-traditional drivetrains, but the majority of choice when you're doing a drivetrain, the recommendation is pick your drivetrain before the season starts. and then just deal with it. So if you guys go into the season next year and say, we are going to do Swerve, put in the work in the off season and feel confident about it, it's been shown year and year again that there are always a way to do Swerve. Even in 2016, when we thought that was the most punishing year to do Swerve, teams did it and figured it out. And so it allows you to spend less time deciding and more time designing to fix what might be some of the weaknesses of Swerve. And so that's where I would highly recommend that you decide as a team before next build season that you're going to do Swerve, and because you're gonna be more successful if you can get everyone on board and eliminate that 1 week of should we build a Swerve, should we build a tank bot, because you already know whatever happens, you're gonna figure it out and you're gonna make it work. A lot of teams, some teams, I know will always do tank. They go into the season and they know they are not going to look at any of these others. And where the team is right now, the choice is between Swerve and tank. All the others are pretty much suboptimal because Mechanum is great for some simplicity, but if you know how to do Swerve, Swerve is just usually better. And so that's why deciding what you want to do before the season starts saves that time. You may think, well, if the game hasn't been released, what if it's crazy and we don't know how to do with it? That's the fun of it, is if you've decided on it, you can just jump into designing instead of spending a week and a half trying to debate if you want to do it or not. Other questions?
One question about the vector addition. So whenever you're adding on the rotational vector, you really only have 2 options for that vector, right?
Yeah,
And
it's
then
always going to
depends
be
on the dimensions of your drivetrain, what that is.
Yes, because you draw this circle for the wheel, and if you have a symmetric rectangle, it's going to be the same for each one, just flipped. But what Stuart is saying is that this vector is always going to be along this path. Its magnitude is just going to change. So if it's positive, it's going to be in this direction. If it's negative, it might be in this direction, depending on how you define it. But for the rotational vector, it's always going to be in this direction that you're adding onto. And that's where I think it's so interesting, this solution, that you're always going to have some component in this direction and then some other random component in another direction that you're just going to add together, and that's going to give you your final output vector.
How did you do the breakdown of what was or I guess a better question is, what did you pass to each Swerve pod in code? Like, what was that high level value that you gave it? Did you give it that final vector? Or
we gave it, so by the position and speed that we're giving it, we gave that as 2 things. One is an angle from 0 to 2 pi. We did a lot of things in radians. And so that was the absolute angle that it had to go to, and then a speed. And the Swerve pod would independently decide. It would do the smart thing of, it knows it would have to find the shortest path and know if it needed to reverse its motor or not. I'm actually going to pull up the 2018 code. So, from the robot high level, so this is the robot code. And if we go through...
Hey, John, could you drop the resolution? Yeah, okay, yep, there you go.
That's still readable, everyone?
Yeah.
Yep.
Okay. So, we go through and in our teleop periodic, the first thing is we do drivetrain. We give it a system state, either if it's in a high level, hey, this is what you need to be doing. And then from here, we then say, are we in field centric or are we in robot centric? And depending on that, we then say, hey, drivetrain, this was the high level call, was Swerve. We give it a forward, a strafe, and a rotation command, and then we tell it what coordinate system it's in and how that scaling is. So this was our generic command that we used for everything. So anytime the drivetrain was moving, somewhere there was a swerve call that was giving 3, the forward, backward, the side to side, and the rotation, and then it had to tell it what coordinate system and then how to control it. And then as we go through back into our subsystems, the drivetrain, it has its 4 pods. It then it holds the motor controllers to pass down to the pods themselves. And so then what happens is we instantiate them all, where we tell them what number Swerve pod are you, and then we also give them their motor controller, because the drivetrain does not control these; it just owns them so that they can be passed down to the Swerve train. The Swerve pod. Then if we actually look to the call, so Crab Drive is a private internal call. This was just, it would calculate, this does all the vector math for us and sets it. So we have a drive constant and then the gear constant. And so then when we actually set them, we go set pod and we give it the drive and then the gear. And so it's given 2 things. This is the speed and this is the angle from 0 to 2 pi. So this is the call that you saw, which at the end calls Crab Drive itself. So that's another advantage of object-oriented, is we have this public-facing call, which can do a lot of things. This is a very generic function, but then internally it decides what to do with itself with this own private call that helps make sure that it restricts access to make sure that you understand what is calling what, and that there's not a rogue file somewhere calling directly to motors. So it helps give some more control. And then if we go down to the Swerve pod level, the Swerve pod, it sets itself up. This is our set pod. This is where it takes the speed. It converts the speed in, this is feet per second, to it's called units per second, which is just the generic encoder units. So the velocity set point that we want, and then the encoder set point is that fine steer position that we were looking at, and we give it that angle from 0 to 2 pi. So if we look at fine steer position, we can see it takes in a wanted in radians and then returns the encoder position. So that's an encoder click. So the encoders are from 0 to 4096, and so we gotta basically map where we are. And so it has the wanted angle and it knows where it is, so it gets the current encoder position, and then it goes through and does our logic of understanding where it wants to go. Does it need to reverse the motor itself? Because then when we actually when we set them, these are all our getters and setters. When we actually go through to set, we do drive motor. We set it to the control mode velocity. We basically say, hey, you're in this PID loop, and then here's your velocity set point. So we actually don't have to have our PID loop inside of this file at all. We do it all on the talons. And the same thing with the steer motors. There's just one thing of basically, if the speed is equal to 0, don't change the position of the motor. This is there were some weird things with, if you aren't going anywhere but you have a different angle, you don't actually need to spin it around. And there were a couple things with how our autonomouses worked that this code just helped reduce unwanted movement of the motors. Any questions over looking at some of this code, how it works, or anything in the presentation that we went through?
From a driver interface side, so I know that the way we do it is we use one stick to basically set the rotational speed. Have we ever thought about using one stick to set like the heading of it? So like if we take that left stick and point it like forward, that's like forward on the field, and then it just holds that.
Yeah, that is another way to do it, is because this is controlling at a velocity level, but you're talking about controlling at a position level, which would be a really interesting solution as well. That we did in autonomous a little bit. There is an autonomous controller that we would command position wise, but that could be an option for the driver. It's again, the goal of the programming team is to make it easier for the driver. So if the driver finds that more natural, then definitely code that up. I know some people find this a little bit easier, but that is what Stuart's talking about. Is basically if you push the stick, let's say to the right, instead of the robot constantly spinning, the robot would just spin to the right and stop. And so it would basically have the heading, or the where the robot is pointing would be now controlled by that. And that would be another way to do it. You'd have to have a higher level loop in the robot class that would help command that.
Also, your sticks are backwards. Your right stick should be doing the spinning.
It's personal preference.
No, it's not. There's a right answer here.
This is
There
how I
is
drove
only
it.
one right
So
answer. Well, you're
this is
wrong.
how I drove it. I know it's backwards, but it's how I did it.
Have you ever played a video game?
I know. Everyone tells me this every single time, but this is the setup that won this team a blue banner. So maybe I'm
Okay.
superstitious.
Multiple maps, each one for a different driver.
Yeah. If no one has other questions, I'm gonna just kind of tell a quick story then of the 2017 season a little bit more about some of the heartache, I guess, of that season. So this robot in the results section, it looks pretty good. Like we did stuff. If you look at our overall record, we go to the first competition. I'd say we drove maybe a quarter of our matches. The other time, we either were dead because of an electrical failure. We also had these really cool bumpers, which looked cool, very bad bumpers. They were originally held on with this really interesting system of, if you think on like the front of a toolbox, that type of latch that comes up and over, we had those types of latches that would latch them onto the robot, which made them really fast to change. So fast, in fact, that it would also happen on the field. And if you have a bumper fall off on the field, that e-stops you. So when we weren't dealing with drivetrain issues, our bumpers were falling off all of the first competition. So that was competition 1. We came back and you're like, okay, we need to fix this. So we decided, you can see there's these little metal brackets. We just bolted the things on, and that's what we do now, is we just bolt on the bumpers and we have reversible fabric. So it's like, bumpers are not the place for you to innovate in FRC. They are not the thing that you want to try experimental things with. You want your bumpers to stay on, and you don't want to be troubleshooting your bumpers while your other systems are failing. So that is one of the things that we learned from that, and just solidly mount your bumpers. So we go into the second competition. We think we figured some stuff out. We're like confident. So we get there. We drive maybe half our matches this time. And this was due to some more control issues. Again, the electrical wiring was an absolute mess. The second competition was also where we did 2 full Robo-Rio swaps this year. The first competition, we had the ground air. The second competition, we're pretty sure we had enough magic robot dust, aka metal shavings, in the Robo-Rio. So we unplugged the entire thing and we're literally banging the Robo-Rio to get the dust out. And yeah, and so that was stressful. So redoing this electrical system about 2 times over, and just lots of issues, constantly browning out. Like, we would drive for 10 seconds and then we would move too fast and then the system would just die. Like, going through and watching match video from our first 2 competitions was rough. We didn't get picked for elims for either competition. So by some magic, we won the Quality and Creativity Award at our first 2 events. I think those were mainly just because we tried Swerve, not anything for our execution, really, because the execution was, from a field standpoint, kind of pitiful, but we learned a lot. And going into state, we were number 36 in the state, and state is usually the top 33 teams, so we were 3 teams out. So we were pretty sure after our second competition we were going home and we thought, this is it, this is the end of the season, we are done. And so that was quite frustrating. Then we get a call on Monday, the week of state, so like load-in is Thursday, and we get a call and it's like, are you able to go to state? This was a very cryptic thing, and we were like, yes. Then we get the email the next day. So we figure out we are going to state the week of. So we roll up to state, and we had been still kind of working on the robot, even though the season we were still kind of holding out hope, because basically what was going to have to happen was 3 teams were going to have to drop to say that they couldn't go for us to be, because we were still technically waitlisted. So then we're the last team in, like below the last team in, teams dropped for us to get in. So we get in, and by this point, this was the first competition that we brought that checklist to. So we brought a checklist that looks kind of like this to that competition. And we had redone the electrical system. And we were a lot more successful. We were able to drive almost basically for the entire event. And we finished up ranked 13th. And so we were like, yes, we're finally going to get picked. But the teams were still kind of afraid of us because we were such a liability at our first 2 competitions that we actually went all the way until the second round, getting picked up by, was it the 5th or the 6th seed captain?
I believe it was the 6th seed captain.
6th seed captain. So we get picked up as the 3rd bot, even though we were ranked pretty well and had been doing pretty well in quals. So we go into it, and we go into quarters, and so we're up against the number 5, and so trying to get that upset done. And then we go into semis, a little bit more nervous of just trying to make sure that the system holds together, because we didn't think that we were going to get anywhere close to that. In fact, one of the jokes going into this season, going into state, was 33 to blue, basically saying, hey, we're going to go and we're just going to knock it out as a joke. And then slowly, as we were getting closer, as we won semifinals, we were going into finals, and it just was such an amazing experience. Got to move the pit into the main gym. And our system, for once, was not having issues. We actually had a couple people on our alliance that were having some issues, and they caused most of the drama during elims. But our system was actually very solid, which was we attribute that a lot to being very, very strict with our checklist and making sure that we do not leave the pits unless that checklist is done. Going through and hand checking every connection on each Swerve pod before every match. That was part of it as well. And just trying to set ourselves up for success with that. And the finals match went to a tiebreaker. And actually the clip that we watched earlier of the homing thing, that was from tiebreaker 3 where we actually won. So it was this crazy season of a lot of failures, learning so much to then be able to come out and show it. And that's been one of the things that our team has kind of taken to heart a little bit, is like build a robot that can get better as the season goes on. I think that's one of the goals, is that you should have your best robot at state, and it's okay if you stumble a little bit at the first competition. It's that learning and that journey and that process that gets you there. And so that was a really formative season for this team, because before then we had been very much one of those that when you look at the alliance sheet and see, oh, team 3176 is with us, it was kind of like, okay, this is going to be either a mixed bag or going to be a rough one. So now when people see our name on the alliance sheet, I would like to believe that it's more of like, that's the good team, that's the team that can do Swerve. And that there's more respect in that we would get picked for elims now based off of our team number, which would not have been a thing 4 years ago. If anything, it would have been very much the opposite. If you guys ever have some time, talk to Dan about the 2014 season. He has a lot of good stories about some of the mishaps from then. So it was just a lot of learning, and I try to tell these stories and keep it interesting because you don't want to go through that type of season again. It is not fun or inspiring to sit through an entire competition where you drive a quarter of your matches and get E-stopped in over half of them. Don't do it. Try to learn from some of this and keep going forward. Any questions over that or other questions about random team history?
Well, with that picture that you have up there, you see how the motors were pointed down towards the ground?
Yep.
You noticed how we had to replace the wire ends on those motors every once in a while?
Yep.
That was one of our problems that we'd run into also. And then also the encoder wires would hit stuff on the carpet, and then swerve drives would lose where they're at from hitting stuff on the ground.
Yes, I don't have a photo of it, but I think it's still in the shop. You can find one of these wheels that what happens if you drive a match with one wheel in a locked position? Because you might think, oh, if I lose steering, that's okay on one wheel. I'll still be able to just move myself around. And that is true. The drivetrain will continue to move around. But what happens to that wheel is the wheel will get worn down because instead of rolling, it is just burning basically. And so there is a wheel in the shop that has gone all the way through all this rubber, flat all the way into the black. And if you find that, that's a little artifact from, I think, Worlds in 2017 on a practice match where we just drug a pod all the way through. So that's why it's so temperamental that if you lose any of these things, the system can be very delicate. But I would say look at the 2018, look at the 2019 season. Much less drive failures, much less things going wrong. And you can do a lot more with Swerve that you can't do with Tank.
I have a question. Can you go to slide 18?
Yep.
So, how much time do you think could be gained by optimizing the way in which we turn?
So the biggest thing, what Chris is asking about is like how much time do you save by taking that shortest path or figuring out the best way to do it? And the answer is quite a bit because the steering motor is much slower than the driving motor. And so because you want to have a bit more accuracy, imagine if you're trying to command something and it just is flying around really fast. It's a lot harder to control. So the steering motor is usually geared in a way that it's going to be easier to control, which means it has a lower max speed. And so you save a lot of time by going the shortest path, but the biggest thing is the behavior of the robot. If imagine you're driving straight forward and then you pull to straight back, not only is there a delay, but the motor, the bottom wheel is still spinning. It still is thinking that it's in the correct direction. So if we think about this diagram right here, the robot operates under the assumption that it is always in the right direction. The wheels are always pointing in the right direction. So that means the wheels, as they're moving, are moving through wrong corrections of this. And that means that the robot is actually going to do a little bit, it's going forward, it's then going to go around and then back. And so that action is kind of unpredictable because you're not going through what the system expects. Especially if you're doing fine motion. Imagine you're trying to line up to something, like in this year's game, trying to line up to shoot or something, and you're trying to go back and forth. Imagine if you're just spinning. To spin from one side, turn from one side to the other, that requires, if you're not reversing your wheel speeds, that requires the wheels to move a full 180 degrees, which means that your robot is not just going to be spinning on one spot, it's kind of going to be shimmying around. And the problem is that it's going to be doing that in an unpredictable fashion. And so that's why it's so important that you try to reduce the amount of time that the wheel is not in the right correction. So basically, what I'm trying to say is, like, for example, if I'm pushing straight forward and then I immediately go to the right, the robot assumes that it's got the correct thing. It does the calculation that the wheels can spin instantly. Because for the most part, usually the wheels can move pretty fast. But if I have to go the long way around, that's going to start to actually affect how the robot moves. So that's why it's so important that you do this math and find the shortest path to go there.
This is more of like an opinion, but what would you say is the hardest part about programming Swerve?
That's a really interesting question. So a lot of people think that it's all of this, that this is really hard to do. But the thing about this is there's so many resources out there already to do this, and I'd say that the vector part is not as hard as you make it as it looks. There's a lot. This paper basically walks you through how to do it in a very approachable way, and so that part I wouldn't say is as difficult. I would say some of the things that starting at just the swerve pod level, because this was the result of an entire season of figuring this out, because we started exactly like I kind of said, of like always going counterclockwise and then figuring out, okay, how do we figuring out this logic, and then once you figure out the small portions, I'd say the biggest challenge is, where's that slide, putting it together into a system. How do you design architecture that is going to seamlessly pass the information that you want to every single part? And one recommendation I would have is do not use the stock WPI Swerve class. The reason is that you're not going to learn as much. I think there's a lot of good at looking at how it works, but I think there's a lot of learning that can be done in how you put together a system, and there's more flexibility in if you write it yourself, because then you're going to be able to confidently talk about it, not only to judges, but it's going to give you that experience going onward into college, into jobs, being able to design a system. Swerve is a very complicated system, but it's not so complicated that you shouldn't try. And the biggest thing is that you also have mentors there. You're not doing this alone. Swerve is a great crossover point that pulls in a lot of things, and requires you to have a good understanding of a lot of different things. So that's why this integration is the hardest level, because you need to know, well, what are the controllers doing on the Swerve pod, and then how should I understand how to design an architecture so that the drivetrain is not going to try to command something that's impossible for the Swerve pods to execute. And then understanding how do I get controller information to the drivetrain in a way that the drivetrain's going to work. There's also a stream of camera data that we don't see. How do I take camera data and make it work for the Swerve drive? So that's all very important to figure out. Does that make sense?
Yeah, that works.
What about at a design level, like the design sub-team level? What are the key lessons that you would give to them?
Yeah, so the design of this Swerve pod, this is where there's a lot of interesting challenges. One of them is, you see this encoder, it's on the output shaft of this motor, but it is run through a gear to actually spin the Swerve module around. And so that gear is a 1-to-1 right now. That means that if we are looking at the output of this motor, it's the same as this gear. And so that means that our absolute position is great. We know exactly how we're doing. The problem is there's how do you design an encoder setup if this isn't a 1-to-1? Let's say the steering motor is geared down way more. We can't just measure on the output shaft because we're back to the same problem of we only know relative control. So from a design standpoint, how do you still have controllability and understand where all your parts are? The packaging of it is the biggest thing. Is how do you package this in a way that is light and robust? So fitting everything into this little box was definitely a challenge, and there's looking into going from gears to belts to reduce the backlash in the system. Because that's another part of controllability is gears have this interface. It's going to be kind of hard to show unless I pull up. So if you see this interface between the two gears, there's going to be some amount of slop between the two gears where one teeth is hitting the other. Where if I move it, I can move this gear a little tiny little bit without moving this gear. And that adds for every gear in the system. And so that means that there's some control where you can be spinning this shaft very, very precisely, but that might be slightly different than what the output is. And so trying to reduce the amount of mechanical slop in the system to make it more controllable and make it more accurate. because that's a big part of it. And weight is always going to be a thing. The nice thing about Swerve is it lowers your center of gravity because you have all these heavy motors down low spread far out on your frame. So, like, for example, a lot of the weight is concentrated on the outside perimeter, so it means you're very stable, but it is also a lot of weight. And so that's always going to be a mission for the design team. Is how do I make this lighter? How do I make it not take up as much space? Why do you do Swerve? Nowhere on this list is because it wins you regionals. It is not all. You're going to read a lot of advice out there that might say the best competitive choice is to always build a tank bot, and that might be true. But there's other goals that I think are important, and I think are important for this team. One of them being brand and identity. Being unique is really important and a way to distinguish yourself. And then the student engagement, this journey of building a Swerve bot is going to teach, it requires systems to work together and requires people to have more broader knowledge bases. And so that's why I think Swerve is such an important tool. It's it's just something that if you can decide on in the off season to do this, that you are going to have a successful season and are going to be able to put something together on the field that is very impressive, because you decided to do it in the off season and because you're not starting from scratch. That's the biggest thing, is learn from the past but also continue to understand it and work through it. So it's not like you're starting from zero. This team knows a thing or two about Swerve, and has done it before, especially in the mentor base. You guys have a lot of really good design mentors that have gone through this and know some of those challenges, and so that's where there's a lot of opportunity for the team to improve and to continue to build that brand and continue to engage a lot of students in this. So thank you all for listening, and for your questions. As always, you can always reach out to me on Slack if you have any other questions or want to know anything more about how our team did this, or any other resources with Swerve. So thank you all.